So I was scrolling through YouTube one day and I came across this really cool video of this T-handle in space. I found a really great explanation video by Veritasium, who has an explanation based off Terence Tao's submission to a math forum, one of the greatest mathematicians alive, and I wanted to try to explain it in under 3 minutes. To understand this phenomenon, we have to first understand a few concepts in physics. I'll meet you over there. So in linear dynamics, we analyze forces that are acting on the center of mass causing the object to move like this. But in angular dynamics, we analyze forces that are acting away from the center of mass, causing it to rotate and have torque. Now back to the linear dynamics, or the linear world, we sometimes ask, how much does this object weigh? Well, we answer with how much mass it has. But in the angular world, we don't so much care about the mass as much as we care about the mass distribution. So that's every single point, its mass and its distance away from the axis of rotation. So that's where it's rotating about. And when we sum these all up, we get the moment of inertia. So that's like the angular equivalent of mass. So now that we understand what moment of inertia is, let's apply it to how we find different unique axes of rotation. So we have an object like this sphere, right? A sphere has only one unique mass distribution, so it has one unique axis of rotation. If we have something like a cylinder, there are two unique mass distributions, so there are two unique axes of rotation. Lastly, the third type of object is a lot more interesting. Since there are three, you have one axis pointing towards you, one axis pointing above, one axis pointing across. For the one pointing towards you, we see here there's a lot less mass, and it's a lot closer to the axis of rotation. If we look at it from this way, right, so pointing towards you, then we have a lot of mass around. It's all rotating. So this is stable, and this is also stable, right? Now, if we look at the intermediate axis of rotation, so this way, well, we have the large amount of mass that's far away from the axis of rotation. So in a rotating frame of reference, we have centrifugal forces that point outwards. So this balances it out, and it's a reason it spins. Let's see what happened there. We expect this to spin about the axis, but what really happened was, as it was spinning about the axis, it also rotated a half turn on the lowest moment of inertia. The reason for this is because any deviation away from the axis of rotation will cause the light mass here, or the mass closer to the axis, to also develop its own centrifugal force depending on the distance away from the axis of rotation. So as this accelerates, it's going to eventually reach its maximum and eventually slow down till it reaches a half flip. So putting it all together, we get a full spin and a half flip. So why does this tennis racket problem matter? Well, in 1958, the US launched their first satellite, the Explorer 1, into space. And it looked something like this. It had a cylindrical shape with antennas protruding out, and as it was spinning about this axis, these antennas whipped around and eventually dissipated enough kinetic energy for it to start spinning on an axis with the largest moment of inertia, causing it to eventually crash back into Earth. So this goes to prove how many variables scientists have to consider in space travel, but when they are successful, the effort is well worth it.